All right, let's dive in. Today we're talking about one of the most powerful tools in all of mathematics, a concept that's absolutely key in precalculus and, believe it or not, is the secret backbone of computer science. We're talking about mathematical induction.
But first, just think about this question for a second. Really think about it. How in the world can you prove something is true for every single number, all the way to infinity? You can't just check each one, right? You'd be there forever. Well, it turns out there's this beautifully clever way to do exactly that.
So here's our game plan. We're going to start with a really simple intuition, the infinite domino run. Then, we'll get into the 3 formal steps you need to know. We'll see it work with some real proofs, talk about the common traps to avoid, and then we'll see why this whole thing matters way beyond your math class.
Okay, so before we touch any formulas or variables, let's just get the core idea down. And honestly, it's as simple as playing with dominoes.
This right here is the whole concept in a nutshell. If you want to be sure that an infinite line of dominoes will all fall, you don't have to watch them all fall. You just have to be sure of 2 things. 1, that you can knock over the very first one. And 2, that if any given domino falls, it's guaranteed to knock over the next one. If you can prove those 2 things, you've proven the chain reaction is unstoppable. It has to go on forever.
Now let's translate that super simple domino idea into the formal language of a mathematical proof. We're taking those 2 actions and turning them into 3 concrete, rigorous steps.
Okay, so step 1 is the base case. This is easy. It's just pushing over the first domino. We prove our statement is true for the first number, which is usually n equals 1. Step 2 is the inductive hypothesis. This part feels a little weird at first. You just assume the statement is true for some random domino down the line. Let's call it domino k. And then comes step 3, the inductive step. This is where the magic happens. You use your assumption from step 2 to prove that if the statement is true for domino k, then it must also be true for the very next one, k plus 1. That's what proves the chain reaction.
So putting it all together, that's what mathematical induction is. It's this superstructured technique for proving something is true for all natural numbers by first proving a starting point, the base case, and then proving that the chain reaction will carry on forever.
All right, theory is great, but let's actually make some dominoes fall. This is where you really see the power of these 3 steps. We're going to walk through some classic examples that you will definitely see in precalculus.
First up, a classic. You've probably seen this formula for the sum of the first n numbers before. But have you ever wondered how we know for sure that it works for any n you could possibly think of? Well, we're about to prove it. Okay, let's break it down. The base case for n equals 1 is a piece of cake. The sum is 1, and the formula gives you 1. Perfect, it holds. Now, the inductive hypothesis. We just assume the formula works for some number k. Now for the big finale, the inductive step. We look at the sum all the way to k plus 1. See that first part, the sum up to k? Well, thanks to our assumption, we can just swap that whole thing out for our formula. From there, it's just a little bit of algebra, find a common denominator, factor things out, and look what we get. We get the exact same formula, but with k plus 1 plugged in. We just proved that if the kth domino falls, the k plus first one falls too.
Okay, let's try a totally different kind of proof. Induction isn't just for formulas with sums in them. We can also use it to prove properties, like showing that some expression is always divisible by a specific number.
So once again, the base case is super easy. For n equals 1, we get 3 minus 1, which is 2. Is 2 divisible by 2? You bet. Now we assume that 3 to the k minus 1 is divisible by 2. So for the inductive step, we look at the k plus 1 version. And here's the clever trick. We rewrite 3k plus 1 minus 1 as 3 times 3 to the k minus 1 plus 2. Now just look at what we've got. The first part, 3 times 3 to the k minus 1, has to be divisible by 2 because we assumed 3k minus 1 was. And the second part is just 2, which is obviously divisible by 2. If you add 2 things that are both divisible by 2, the result has to be divisible by 2. And just like that, the proof is done.
All right, for our last example, let's tackle something a little bit trickier, an inequality. The process is exactly the same, but the algebra can require just a little more creative thinking.
The base case for n equals 1 works, because 2 is definitely bigger than 1. Then we assume that 2 to the k greater than k. Now for the inductive step. We start with 2 to the k plus 1, which is the same as 2 times 2 to the k. Now because of our assumption, we know 2 to the k is bigger than k. So 2 times 2 to the k must be bigger than 2 times k. Great, but our goal is to show that 2 to the k plus 1 is bigger than k plus 1. So if we can just show that 2k is bigger than or equal to k plus 1, we're golden. And a tiny bit of algebra shows that, yeah, for any k bigger than or equal to 1,
2k is always bigger than or equal to k plus 1. The chain is complete. The proof holds.
So we've seen just how powerful induction is when you do it right, but it's also really easy to mess up if you're not careful. Let's quickly go over the common ways these proofs can go completely wrong. Think of it as how not to set up your dominoes.
These are the big 3 mistakes. First, skipping the base case. That's like setting up an infinite line of perfect dominoes, but never actually pushing the first one over. Nothing happens. Second, not using your inductive hypothesis. This means you haven't actually proven the connection between one domino and the next. They're too far apart to hit each other. And finally, circular reasoning. This is basically just saying, I know all the dominoes will fall because I'm assuming they'll all fall. You haven't proven anything at all.
So you might be thinking, okay, this is a cool math trick, but is it useful for anything else? And the answer is a huge, resounding yes. This way of thinking is actually fundamental to the entire digital world we live in.
This is the mic drop moment. Think about a recursive computer program, an algorithm that calls itself. It always needs 2 things: a base case to tell it when to stop, and a recursive step that works on a slightly smaller version of the problem. That structure, it's a perfect mirror of mathematical induction. Programmers use this exact same logic to prove with mathematical certainty that their code will work correctly no matter what you throw at it.
And that's really the main takeaway here. Mathematical induction isn't just a formula to memorize. It's a whole new way to think logically about problems that seem impossibly big. It's your personal domino effect for proving things you never thought you could.